University, and I'm contracted by Grand Canyon National Park. So I've been working here about 2.5 years, a little bit over. So I work with a team of hydrologists, and we monitor different sites within the canyon. We are also kind of in charge of our cave resources. And you will find out in this presentation, the caves and all the water you see in the Grand Canyon are very connected. So the topics I'm going to be covering: what is karst and where is it? And what do we do here at Grand Canyon Hydrology? And what are our current, past, and present projects? So in a karst environment, the key thing you have to have is a type of rock that can be dissolved by water. So here at Grand Canyon, we find that mostly in limestone. So the Kaibab limestone and the red wall limestone, those are very good examples. So here we have a diagram. What's really important about karst is that as it dissolves, it creates these passages, which are like a network of pipes even. And you get these point infiltration points on the surface, which delivers water from the surface, to the spring very quickly. Whereas in most systems, you have diffuse infiltration, and it's a much slower process. So, there we go. So here at Grand Canyon, we have that same system with lots of karst dissolution, but it's a little bit more complicated because we have a sea aquifer, the shallow aquifer at the top. Water enters through sinkholes. They travel down through faults and fractures, and they exist in this aquifer here. Then through faults and fractures, they travel through these non-karstic layers, these impermeable shales and mudstones, down into the red wall aquifer, composed of the red wall mauve limestones. And in this aquifer, we have Roaring Springs. So Roaring Springs is a spring that emerges from our aquifer. It's very important. It is currently the only water source for all of Grand Canyon National Park, so we really care about this spring. Sea aquifer does have springs as well. This is Robber's Roost. It is a historically important site, important for archaeological and for biological resources, but it's a lot smaller than that other spring. Oh, clicker. We also have many caves in the park. So Grand Canyon is a cave park. This is something that a lot of people don't know. We currently have over 400 known caves, and only a fraction of the park has actually been thoroughly explored and have those caves confirmed. There's over 1 million acres of karst terrain in Grand Canyon, and over 85 miles of mapped caves. The largest being Double Bopper, which was recently connected to another cave. So this number of 35 miles is actually far smaller than the current number. And you notice the only caves with more mapped caves, or the only national parks with more mapped caves, are all the national parks with cave in the name. Oh. This is... it's being frustrating. Okay, so now I have some pretty pictures of caves, just to kind of show you the variety of caves that we have in Grand Canyon. A lot of them are really large. We have some really expansive caves in Grand Canyon. Some of them are very small and hard to access. We also have a lot of dry caves in the park, and these often contain really important, many archaeological resources as well as paleontological resources. They're also very important habitats for many animals in the park. We also have very wet caves. This is where that groundwater comes into this karst system and is actively forming this cave. I don't particularly know these in the photos. There's also lots of really important mineralogical resources. We have all these delicate cave formations. Yeah, so it's very important to protect these caves. And most of the caves are actually mapped and observed by volunteer research groups. So with the hydrology at Grand Canyon, we are involved with that, but our main job here is to monitor the water coming out of these caves. So we have 17 stream gauge sites in the canyon where we have transducers measuring temperature and water pressure. 6 of these are within wet caves, and the rest are all in creeks throughout Grand Canyon. Our typical site maintenance involves measuring water quality, taking samples of the water, measuring water discharge, so how much water is coming out of the creek, and downloading all of our data from those data loggers. So why are we interested in this? Well, one, I mentioned Roaring Springs. It's currently the sole water source of Grand Canyon. We want to know where that water is coming from. Is it safe to drink? How's it doing? Our future water source, so they are currently working on moving the water source from Roaring Springs to the delta of Bright Angel Creek. And Bright Angel Creek, the perennial base flow, is entirely fed by these karst caves and karst springs. And all of the backcountry perennial streams in Grand Canyon are also fed by these karst springs. So it's all connected and definitely important if you're seeking water in Grand Canyon. So now on to project updates. In general, our projects are located at the Kaibab Plateau. Oh, it's giving me a red light. That can't be good. Oh, there it is. Yeah, so Kaibab Plateau is located here on the, on the north side of Grand Canyon National Park. The Kaibab Plateau is an elevated region that receives a lot of rainwater. It's actually a temperate environment. So all of that rainwater percolates down through the system, like that diagram I showed you earlier, and then it's dispersed throughout springs and emerges in these springs within Grand Canyon. So most of our research focuses on this region, and a big project we had between 2015 and 2017 was the dye trace project. This project was one of the largest dye traces ever attempted. We had 5 injection sites into sinkholes. We had 3 dyes recovered. The maximum depth from sinkhole to where the dye was received was almost 200 meters. So that's what makes it one of the largest. And the straight line distance from sinkhole to where it was received was almost 40 kilometers at its greatest point. And the travel times from when the dye was injected in the sinkhole to when we received it was between 1 and 3 months. So this is a map of where that dye trace occurred. These circles up here are the 5 sinkholes that the dye was injected into. These triangles all along inside the canyon were where our dye receptors were placed and where we monitored for this dye. And the first dye that we received came from this red sinkhole. We found that dye way over here in Deer and Tapeats Creek and way over here in Vasey's Paradise. So pretty widespread, also here in Shinnemoo. And then this yellow dye, also found it in Vasey's Paradise and all along Bright Angel Creek, but not in Roaring Springs. And this blue dye, which arrived in 2017, that was from our 2017 dye trace, we did get a hit in Roaring Springs, so that was pretty exciting. And we also received dye in the Nankoweap complex and over at Vasey's Paradise. And ultimately what we learned from this project is that it's an incredibly complicated system. In fact, if you zoom in here, you can see that some of the dyes even cross paths. So it's a system that we still don't fully understand, and we had to postpone it last year, but we're hoping to start it up again. However, in the meantime, we decided to approach this process from different ways. So one of our new projects is modeling the vulnerability to contamination on the Kaibab Plateau. So the purpose of this is to find regions that might be sensitive to changes in water supply, or we want to find out which regions are actually important in supplying this groundwater. So potential contamination could come from humans or from wildlife. As the climate changes, reduction in snowpack. Snowpack is currently the largest feeder of this groundwater system. So if we decrease the snowpack, we might see less water overall. And water on the Kaibab Plateau travels really quickly. When you have a monsoon event on the Kaibab Plateau, a pressure surge in Roaring Springs occurs within 3 days from that event. So it's a very fast traveling system. Here's some examples of the sinkholes that we're looking at. Some of them are really large. This is actually a bonfire pit at the bottom of that sinkhole. Some of them are obvious collapse features. Some of them are pretty small, but this sinkhole here had a fire truck put water in it, I think about 500 gallons, and that was all drained within 7 minutes. So don't judge a book by its cover. Here's another example of sinkholes draining in action. So on April 25th, 2012, right as snow melt pretty much ended, the sinkhole was completely filled with water. And 7 days later, it was entirely dry. And you can actually see this sinkhole. It's in DeMott Park, right off the road. It's a dramatic hole. So we were interested in these sinkholes because we know that they drain the water. And we also know that sinkhole density correlates with increased groundwater contamination. So we used LiDAR data to create a sinkhole map of the Kaibab Plateau. We found almost 7,000 sinkholes on the Kaibab Plateau. And in blue here, we have sinkhole density. So this darker blue region has higher sinkhole density. And when we overlay it with faults and fractures, we see that there's a high correlation between the presence of many sinkholes and the presence of faults and fractures. And this actually indicates that these faults and fractures are likely the hydrologically active conduits delivering water throughout this system. I'm going to save questions to the end. Thank you. We used this density and fractures to create a vulnerability map. So this is of the shallow sea aquifer using mostly sinkhole density. These red spots would be your high vulnerability to contamination regions. And for the deeper R aquifer, this includes the location of faults and fractures as well. And you can see many of the regions overlap. Again, that's because the sinkhole density and the faults and fractures overlap. And you see less red in the deeper R aquifer, mostly because it's almost 900 meters deeper in the earth than the sea aquifer. So that's why you see that reduction of vulnerability potential. We also have a master's student working with us to try to better understand the sea aquifer. So he is currently maintaining 28 springs with different sampling sites, and some of them have data loggers as well. And so these red dots here are those 28 springs. And what he's looking for mainly is where does that water come from, what springs are more similar to each other, and then we can use that information to better understand the connection between those sea aquifer springs and the springs inside Grand Canyon coming out of the R aquifer, such as Roaring Springs. And lastly, associated with the moving of the water source for Grand Canyon, we had a few of my colleagues do a groundwater model of the Phantom Ranch Delta here. So that's the Phantom Ranch Delta. This red square is the pumping well where they propose to put this new well to change the water source. And there's a few reasons why this plan has been proposed and is in the works. One, the pipeline is really old and it breaks all the time. It has exceeded its lifespan. This would reduce the amount of pipeline that we actually have in Grand Canyon carrying water. So this new site would pump directly to the south rim, while Roaring Springs would still pump to the north rim. Also, moving this would allow more water to go into Bright Angel Creek for the extent of the creek, so that would help put water back into that ecosystem. And here's just some examples of the models that they showed. So the most important takeaways from the models was that no Colorado River water would be drawn at the proposed pumping rate. This is a good thing. And there would be a maximum 3.4 meter water table drawdown at the well. So this first image here is showing you the water level, and it creates a nice little cone right towards the well. And then even with that amount of drawdown, that pumping rate, you would only have 0.2 cubic feet per second reduction within Bright Angel Creek, which is only 1 to 2% of the base flow. So you wouldn't see a big decrease in the local water in that creek area. These maps over here are showing tracers. So if you put a tracer in Bright Angel Creek and modeled it as it's flowing towards the pump, this is the likely path that it would take. And then if you put the tracers in the Colorado River, you can see some of them dip into the delta, but ultimately go back to the Colorado River, so we're not intaking that Colorado River water. Future projects. So we're currently working on a project to monitor monsoon precipitation and compare that to the spring discharge that we see. And that would be similar to the dye trace, but would not involve dye. So that would be a pretty interesting project. We can go back through lots of years of data looking at the precipitation and the discharge and correlating those relationships. We also are closely following the Phantom Ranch Groundwater project. We just got approved to have a researcher come on and help with the pumping, or with the drilling of that, so that project will be moving soon. And we have other NAU researchers that are doing evapotranspiration studies within Bright Angel Creek and potential geophysical work on the Kaibab Plateau to better understand that conduit system. And hopefully soon we'll be doing more dye tracing. Yeah, exactly. Oh, it all goes to facies, is what he said. All of this, so biggest takeaway, all of the surface water you see here is connected to the groundwater system. So that's why it's important to learn about it. And it's an incredibly complex system, and we are currently doing research to try to understand it better. So yeah, here's some examples of some of the sites and some of the researchers on our team. And some acknowledgements. Thank you, everyone that has helped out with this project. Are there questions? Yes?
Two questions. Number one, if you're increasing the flow of the Bright Angel Creek, would that increase the danger of flood damage at Phantom?
No, because most of that is from flash flooding, which is overland flow. So the amount of water you're increasing the flow, but it's only by, I think, 2 to 3 cubic feet per second. I do not know the exact number, but it's fairly low.
Number two, if all these guys show up at bases, would you expect bases to have a larger flow than the springs? And from my experience down there, that doesn't seem to be the case.
So the system is very divergent. So you start with a point and it branches out in many directions. And eventually, I guess it's converging at Vases. That doesn't necessarily correlate to the high flow. Vases is rumored to fluctuate a lot in the flow, but yeah, it definitely varies. So because the system is so complex, that does not necessarily correlate, but good observation. Yes? Yes, I can. So it is evapo, that part is evaporation. Transpiration refers to how much water the plants are taking up and then releasing through their leaves. So every day you actually have a fluctuation in the water level just from the sun hitting the water and the sun hitting the plants and the plants drawing up water. So they're looking at that relationship between how much evaporation and plants are taking up and how much is the actual base flow, the water going through the creek. Yeah? Uh-huh. From my understanding, it changes seasonally. So during snowmelt, you probably will see all 3 waterfalls coming from Vases. And as the water level goes down, you end up seeing 2, and then it'll dry up to even 1 or just a trickle. So it fluctuates. If you're normally seeing it out of 1 and then not others, I'm not really sure why that is. But I've definitely seen it where it has 3 waterfalls and then it only has 1. So it depends on the water level. Okay. Other questions? Yeah. Ellen? It's... Oh, okay. Yeah. Maybe repeat the question.
The question was whether or not the pipeline project is fully funded yet, and it's not. It's going to take us quite a while to gather all the money. We're still in the process of determining what pathway we're going to take. There was an environmental impact statement, or actually it was an EA, an environmental assessment, that was open to public comment. We've gathered the comments from that. We have to analyze the comments that we receive. The park has to choose the actual alternative that it's going to build based on that EA. The two primary alternatives are replacement in kind, rebuild the whole pipeline, or do the intake gallery at Phantom Ranch. We can't even proceed with that intake gallery until we do the test that Natalie described, to do the drill to see if we can even get the water from that source. If that doesn't work, then we have to look at an infiltration gallery right in Bright Angel Creek itself and consider how we would protect fish and other aquatic species if we use the intake gallery. But let me ask you all a quick question. Why would we not draw water from the Colorado River? We don't have the rights to it, so that's the number one primary thing. So we still have a long way to go. Entrance fees that the park is gathering will help pay for that pipeline, and then also funding from the Washington office and stuff. But it's a long-term process. Probably what we will start with is doing the work. When we choose the alternative, then there's work that we can do on the south rim to put in new pumping stations for sanitation of the water and things of that nature before we ever actually go into the canyon. But there's a lot of work to be done yet still, and we don't have all the money. That's a technical question. I personally don't know. But, you know, if you have other questions about the pipeline, you can come see me afterwards. Natalie can take one more question, then we got to move to the next one.
One, okay. Sorry.
I actually have two questions very quickly.
Oh.
The fault line that you showed in that one picture where you had the dye green,
Mm-hmm.
was the road that goes from,
Yeah. Is it 67? Is that the road? Or 64? It follows that fault line. Correct.
secondly, has there been any, has anybody looked at the effect of forest fires and whether or not fire has any effect on the rate of percolation?
Yeah. Forest fires definitely do have an effect on that because, again, with the evapotranspiration, the trees will be taking it up a lot of the water. There's also increased overland flow, so it's harder for the water to percolate down when you have the forest fires. There have been studies done on that. They definitely do affect it.